Hello everyone and welcome to Physical Science. Today we're going to be talking about circuits and power. Now, quick story. I actually wired my own house and so have some background in circuits and power. There were a little bit of kinks here and there, but you know, overall, I can wire a house. What? Okay, so circuits. A circuit is a closed path through which electrical charge flows, specifically electrons. So a circuit is a closed path through which electrical charge flows. Now what it really is are just electrons. You have an excess of electrons that flow through a wire, through a conductor, and cause some excitation of particles, and then they'll flow all the way back to the positive side. So it is an excess negative charge. And if you remember, likes repel, so electrons repel from the positive side, and it causes a flow of electrons. So in our notes, we're going to draw in a basic battery, just like this. So we got a battery. Boop, boop, boop. So in our battery, we have a positive side and we have a negative side. Electrons flow. So electrons are going to be the ones that are moving. If you were to connect a wire from one to the next, what you would end up with is a flow of electrons. Electrons are going to be pulled from the negative to the positive side. And when they hit something that can be excited, like a filament, it will cause light. So electrons are the things that are flowing from negative to positive. So an electrical current, let's look and move this out of the way. Boop, boop. An electrical current is going to be a flow of electric charge. So it is just charges flowing, just like we just saw. It's electrons flowing from a negative to a positive, but it has to be a closed circuit for it to work. An open circuit is when the current cannot flow. So you have a break in the line. So if you were to take a wire connecting from the negative side to the positive side of a battery, and you were to draw in your notes an open switch. This is an open circuit right here because it isn't connecting back to the opposite side. So there will be no flow of electrons. No flow of electrons means no electricity flowing. So no electrons flow equals no electricity. That's why when you flip a light switch off, what's happening is it's breaking the circuit. So it's opening it up, so then the current cannot continue to flow from negative to positive, turning your light off. As soon as you close or switch it on, it's going to close it, and then it will cause it to recirculate, and we'll have an electrical flow from one thing to the next. So there are two different types of circuits. One is really simple. It's called a series circuit. Series is one thing that comes after the next, that comes after the next, that comes after next in a series. So one after another after another. So this has one loop through which current can flow. You have to go from one to the next to the next to the next. So if one of the lights stops, it cuts off everything. So let me show you what I mean. We're going to draw in a box representing a battery, and we're going to put a negative side and a positive side, and we're going to connect it to a light. So when you connect it to a light, and I'm just going to simplify it as this, it's going to have to flow in here and out here, and then it will hit this and will conduct and will flow in here and out here. So it's one after another after another. So 1, 2, 3 lights in this series circuit. So electrons are going this way. So if they're going this way, what if this light bulb blows out? If this light bulb blows out, that means that you have an open circuit now. There will not be a flow of electrons anymore. So you would end up with something that is open. If it ends up with an open circuit because your filament blows and there isn't electricity flowing from here and into here, these two will go out. So if one goes out, go out. So let's say that instead of one blowing, let's say that one is still, so I'm going to back it up a second. So let's say that instead of that one blowing, we end up with the third one blowing. Does that mean that 1 and 2 will still be lit? No, I just said that if one blows, all of them will go out. So if this one goes out, notice the circuit is open here. So it's going to try to connect, but if you don't have a flow of electrons, there's no electricity. If this is broken, then there still cannot be a flow. You have to have a flow. So if one light stops, one stops, all stop. Okay? Now, a little bit more complicated is a parallel circuit, and that's what your house is, and that's what I wired my house to be. A parallel circuit means that I can flip one light switch off and not have the rest of my lights in my house go off. Well, how? You still have to have a flow of electrons. It is hooked up in something called parallel. So this is a parallel drawn on your battery. You're going to put your positive side and your negative side, so you have a flow of electrons going in this direction. Okay, so then it's got to go through here, and then it's going to come back, and it's going to connect. Okay, so we have flowing electrons. You need to have a path, some path from the negative to the positive. So let's say that this is a path on its own. If you go here, if this light bulb were to blow, then it wouldn't affect these other two. Why? There's a path here. This one has its own path. So if this one were broken in the middle, guess what? This one still has a path. And if this one were broken, it's okay, because this one still has a path to get from negative to positive. Each one has its own unique path. So you can flip one off and leave the rest of them on, because if you flip this one off right here, guess what? It can still bypass it. There's always a bypass. So in a parallel circuit, one light stops, the others will still work. Now here's the exception to the rule. So in a parallel circuit, there is a way to have everything cut. So you got your positive here and your negative here. So if you have a parallel circuit again like this, where you have a light bulb here, and you have a light bulb here, and let's say you have a light bulb here. If light bulbs, this light bulb could go out, two of these could go out and the other one would still be burning. The only thing that could cause multiple of these lights to go out is a break in the actual line itself, not the light bulb. So if you were to break it here, since it's a flow of electrons, would any of the lights light up? Well, is there a path of electrons to be able to get to connect a circuit? No, they would all get stopped here. So if you were to break it here, there's no way for electricity to get from one to the next. But let's say if you broke the line in a different spot. Let's say that you broke the line here. Would this one work? Yeah, you still have a path from negative to positive. Would this one work? Nope, you don't have a path. Would this one work? Nope, you don't have a path. So really, you can break it down to is if path unbroken, if its individual path is unbroken, it will work. If it's not, if it is broken, then obviously it will not work. All right, so in a parallel circuit, the voltage difference is the same in all of the lights. So if you have voltage same in all lights, so you have the same amount of current going to this one as you do going to this one. Backwards, because that's positive, you should be going this way. Same amount as this one is going to this one. They will light up equally as bright. So light number 1 and light number 2 would be of equal brightness. However, in a series circuit, it would not be. Let me back up for a second. In a series, you are losing current every time you go through one of these light bulbs. So this would be the brightest. So let's flip back and let's add brightest. This would be a little less bright, and this would be the least bright. Because they're all got to go through the same wire, so each one is losing a little bit as it goes. That would be bad in your house, by the way. So this is exactly how a house is wired. You'll have some sort of source, a source of electricity coming in from the power company, and then you will be running wires, and those wires will be running parallel to one another. So notice that if I want to turn on this, or if I want this outlet going, it has a path all on its own. But what if I want to use this outlet and not these other two? I can do that. It has a path all on its own. And then let's say I want to turn this on and off, but I want all my outlets to still be working. Well, they all have their own paths. So if the individual path to whatever is on it is unbroken, it will continue to work. And that's why you can turn your light off and have your outlets running, and that's why you can have one outlet working and then not be using the other outlet. So electricity has to have a path to flow on. So electric power, we got a formula for this. This is the rate at which electric energy is converted into another form of energy. Power equals IV. So your power is going to be measured in watts. Your current is going to be measured in amps, and this is current. And your voltage is going to be measured in volts. So whenever you're trying to identify power in a word problem, you're going to look for watts. And we've talked about power in watts. And if you're trying to find current, you're going to look for amperes or amps, abbreviation. And then if you're looking for voltage, that one's easy because it's volts, or V. So P equals IV. So let's try it. I'm going to take P equals IV. If I'm using my triangle, I'm going to do it both ways for you. Power equals current times voltage, or you can plug into your formula. So I write down my variables before I do anything else. I see 9 volts, so 9 equals my V. I keep looking and I find my next thing, and it says 6.67 amps. I'm not even reading the problem because I don't need to. 6.67 equals my amps, and my amps is my current. So how much power does the clock use? So I know I'm looking for power equals question mark. So let me plug in my variables. If V equals 9 and current equals 6.67, then all you have to do is multiply, because if I cover this up, side by side means multiply. All I have to do is multiply 6.67 by 9. If you're using the original formula here, all you have to do is plug in your variable still. So you would say P equals 6.67 times my voltage, which is 9. And you just plug it into the calculator. Done. Moving on. Now the units of them would be watts. Second example, how do we set it up? All right, P equals IV, or you can do your triangle with I times V equals P. So I'm going to look for the first thing that I've got, 60 watts. 60 equals W, which is, or watts, which is power. So I'm going to put P above it. And then it says 120 volt. 120 equals my V. And then it says, what is the current? Current question mark. So I'm looking for my I equals question mark. I plug in my variables. Power on this needs to go up top. Power is 60. My voltage needs to go right here, so that's 120, and I'm solving for I. So if you're using the triangle method, you can see you have to take 60 divided by 120. If I solve it algebraically though, I do 60 equals I times my voltage, and I plug that in, which is 120, because that is what my voltage is. To get I by itself, I have to divide both sides by 120, and that's how you would get to your answer. And current is going to be in amps. Okay? So if you take 60 divided by 120, there you go. All right, everyone, I hope you have enjoyed, and I want you to have a wonderful day with P equals IV. thanks to parallel currents. Ooh, I spelled parallel wrong. Thanks to parallel circuits, we can have electricity. Bye.